Good evening, my dear students. Let us enter into one of the most important areas of plus 1 and plus 2 mathematical areas now. Like calculus, algebra, vectors, we have various branches of mathematics. One of the other important branches we have in mathematics, which takes a very important role for all competitive exams, IIT, JEE, starting from that one to even basic IPA level also. A very important one is geometry part. Now today let us enter into this complete analysis of analytical geometry. Here complete plus 1 plus 2 topics, if we analyze overall various topics what we are going to cover, have a brief look today before entering into the right chapters now. In complete plus 1 plus 2, we are going to analyze straight lines, one more important part is circles. After that, we can also analyze the parabola chapter. After that, we can discuss about ellipse, and we can also discuss about hyperbola, various cases. The complete 2 years geometry part, if we just look into these various chapters, we can discuss about these various topics. The entire plus 1 plus 2 geometry covers these 5 important areas, starting from straight lines to this is hyperbola. Even in hyperbola, other parts also, rectangular hyperbola, special case also we discuss. Now, is there any interrelation between all these chapters, or are they independent? Are they not depending on others, or do we have any common resemblances in all these? We have to analyze before entering into the chapter wise analysis here. If we observe very carefully, the straight lines, circles, parabola, ellipse and hyperbola, even though they appear as if they are different chapters, but we can have very common resemblances, many common points we can find in many cases. So today let us see all those similarities what we are finding in this. To analyze all these, let us start with a right angle triangle. I am taking a simple right angle triangle which is right angled at vertex B. Here in this right angle triangle, just if we are rotating the base about this vertical side, we are rotating the base clockwise or anti-clockwise. If we are completing a full rotation of this here, the three-dimensional figure whatever we are getting by this overall rotation will be forming a cone which is called right circular cone. Because the base is circular, that's why this can be called as right circular cone, in which this vertical line about which the rotation is taken place is called its axis, and the point A is taken as the vertex of the cone. Just based on this simple right circular cone, we are going to define the entire straight line, circles, parabola, ellipse and hyperbola, such different parts of this geometry. How to analyze all these? What is the relation between these conic sections or geometry various areas and this cone? Now let us see in detail in today's part. Now I am selecting a double right circular cone with common vertex and common axis. A very important point is I am selecting a double right circular cone with the common vertex, and axis of these cones is also common. So if you analyze this double right circular cone with common vertex and common axis, with the help of this we can trace out all the curves whatever I have discussed earlier. Here just with the help of a plain sheet, here take the various cross sections of this double right circular cone taken in different angles. For example, take a plain cutter and cut it perpendicular to the axis. If you are cutting this double right circular cone horizontally or else perpendicular to the direction of this axis, one can say very comfortably that this cross section will give you, if you are observing this cross section, that will give you the shape of a circle. So no doubt circle can be taken as a cross section when we are cutting this with the help of a plane in perpendicular direction to the axis of this one. So it is a part of double right circular cone undoubtedly. Next, instead of taking a right angle, if you are taking theta value, this angle of cross section less than 90 degrees, cut it cross. Just if you are taking the cross section in angle less than 90 degrees, if you cut the cone in cross directions, we can find the cross section which is giving you shape of ellipse. So ellipse is also a part of this double right circular cone. Apart from these two cross sections, parallel to any one of the edges, these two are edges, edge 1, edge 2, parallel to any one of these edges, if you are taking the cross section, if you are cutting this, just if you are taking the cross section of the cone, by cutting it parallel to this edge, we can find out the cross section in the form of a parabola. So parabola is a part of cross section of the cone. And one more, parallel to this common axis of double right circular cone, take the cross section, but the condition is we should not take the cross section through the vertex. Without passing through vertex, take the cross section of this vertically, that means parallel to this vertical axis. Here you are finding the cross section which will give you in the shape of this. Simply, if I draw separately here, you are finding cross section in the form of this, which appears as if two different parabolae taken opposite directions. I will come to this in detail about this one, why it is not called parabola, why it is called a hyperbola. This is actually called hyperbola. So circle, ellipse, parabola, hyperbola, all these four different different curves, actually, even though appearing they are different, not even related to each other, but all together we have a common connection in between all these. All these are taken as the cross sections of a double right circular cone in somehow in certain direction by taking a plain cutter sheet and cutting it in different directions. And apart from all these, even we can discuss about straight lines also, pair of straight lines from this diagram. Here, take the plain cutter and cut it through the vertex, exactly through the vertex. If you take the cross section of this one, suppose you are cutting it exactly through this, any direction is not important, but we are cutting through the vertex of this one. Here just we can find out that a slit like this. If you are observing it separately, we can find this cross section in this form, which is giving you a pair of intersecting straight lines. So like this we can form pair of intersecting straight lines, circle, ellipse, parabola, hyperbola. All these 5 different curves are taken somehow as cross sections of a double right circular cone when we are cutting it with a plain cutter in different angles. That is why these all, which is giving you the entire geometry syllabus of +1 +2 IIT JEE, can be treated simply as conics, or in particular we can also call them as conic sections. We can analyze various conic sections in 2 different categories. Here, some of the conics like ellipse, circle, hyperbola, these 3 treated as one type of conics. Here, this circle, ellipse and hyperbola, all these 3 are containing the center, which is called the center. That is why these three called as central conics, and the remaining two non-central conics, we can define them very comfortable. The conics which are containing center can be called as central conics. Here, apart from this, we can take one more categorization, which is depending on eccentricity of the conic, which we will enter into that part in later stages chapter wise. So meanwhile, now at this stage we can take two types of conics. Conics which are having center, conics which are not having center. These are two categorizations we can take right now at this stage. In this complete geometry part, we are going to analyze these various branches of these conic sections, starting from pair of straight lines to hyperbola. And in detail, we discuss various parts of this one chapter wise. Now, as we have discussed just now, we have very similar relations between circle, parabola, ellipse, hyperbola and pair of straight lines. All these five conic sections which are generated from a double right circular cone. That is why the general equation to all these also can be taken with the same equation, which is the general second degree non-homogeneous equation in x and y, whose standard equation now onwards taken as S identically equals to ax square plus 2hxy plus by square plus 2gx plus 2fy plus c equals to 0. Not only they are connected with the common conic sections part, in many cases they have very common properties, including their standard equation. Here all these five curves will take their general form as second degree non-homogeneous equation in x and y. Here these first three terms are taking homogeneous part, which are second degree terms. These two are first degree terms and this is a constant term. So this is taken now onwards as common second degree non-homogeneous equation in x and y. Depending on various cases, the same equation will represent different conic sections, which we are going to derive chapter wise in detail. Before deriving all this, let me give you overall brief idea of all these conditions together here. Here, if the determinant A, H, G, H, B, F, G, F, C on simplification, which will give you the value of ABC plus 2FGH minus AF square minus BG square minus CH square. Briefly, I will call it now onwards as delta. Depending on this delta value, various cases we analyze the nature of the curves, which will be derived chapter wise. Before entering into the chapter in-depth analysis, I will give you brief idea of cases of all these five curves. Here, case 1, delta equals to 0, this determinant is equals to 0, then it is representing a pair of straight lines. The given curve is representing pair of straight lines. Case 2, delta not equals to 0 and x square coefficient, y square coefficient both are equal and h equals to 0. If whenever this delta not equals to 0, AB both are equal and h equals to 0, the given equation represents a circle. We are going to prove all these chapter wise. I am giving brief idea before this. Next one, delta not equals to 0 and h square equals to AB. It represents a parabola. Next, delta not equals to 0 and h square less than AB. it represents ellipse. And finally, delta not equals to 0 and h square greater than AB, it represents a hyperbola. We can have a special case of hyperbola which is called rectangular hyperbola also, in which case we are getting additional condition a plus b equals to 0. We are going to derive all these chapter wise in detail. Overall brief idea I am giving you about the nature of various curves, how to analyze with the help of this second degree non-homogeneous equation. Now, if you have these basic ideas clear, then we can enter into the study of these circles comfortably in detail. Each and every part, micro level analysis we can do in this circles part. So now we can enter into the chapter circles, which is a very, very important chapter for all levels of competitive exams in this +1 and +2, in which we can solve many problems even by using pure geometry applications also. So student must have various basic ideas of pure geometry also to solve the problems of these circles, analytical problems. In this, wherever required we use analytical geometry, and wherever we require we can use pure geometry concepts also, as everyone is aware of basic ideas of circle properties from high school level, like angle in a semicircle is right angle, or angles in the same segment are equal, etc. Basic theorems using, we can do many problems of this circle chapter much effectively than this coordinate geometry. Now, if we think of its definition here, how we are getting a circle as a cross section from a double right circular cone we have seen just now. Now, let us see the mathematical definition of this circle. It is a very frequently finding locus case in geometry. Very frequently we find coming circles in many locus conditions. Among those, the most frequent one is here. Let us see. Suppose A is a fixed point in the plane somewhere and P is a variable point moving such that distance between A and P is always a constant K. If P is a variable point moving in such a way that distance from this A and P is always a constant K, then if you take the path of all such points, joining all these, we are finding a circular one. Therefore, we can take this particular part as the definition of circle. The locus of a variable point moving equidistant from a fixed point A is defined as circle with that fixed point as its center and the distance K as its radius. This is the most commonly finding definition of the circles. Apart from this, we can discuss definition of circle in many other cases where you find some minor errors sometimes. That's why we take this particular one as the standard definition of circle. Here, if A is a fixed point and P is a variable point moving such that AP is always a constant K, is defined as a circle with center A and radius K units. By using this, we take the first standard form of the circle. Center radius form of a circle we can define. If the center is taken as h comma k point, radius taken as some r, some standard value r I am taking instead of k, h comma k center, r radius. If you are imagining for a circle equation, to find out the circle equation here, let us imagine a standard point x comma y somewhere on the circumference, anywhere, wherever you take the point P, this AP distance is always constant r. So here mathematically we get the condition AP equals to r. On squaring both sides, AP square equals to r square. Distance between 2 points apply here. You are getting x minus h whole square plus y minus k whole square equals to r square. This is taken as the center radius form of a circle. The very first result we are introducing in this chapter. Here, center radius form. In all the cases, whenever you know the center and the radius, the circle equation can be taken with this equation. X minus h whole square plus y minus k whole square equals to r square. Coming to the second case. Now, let us take the second case of the circles. Instead of taking one fixed point, here I am taking two fixed points A and B somewhere. These are two fixed points, and P is a variable point moving such that angle APB equals to a right angle 90 degrees, or we can also take it as Pythagoras result, Pythagoras theorem. PA square plus PB square equals to AB square. If a variable point P is moving in such a way that it is forming right angle by this fixed line segment AB, then as we know already, angle in a semicircle is right angle. Wherever this P moves, condition given is angle APB is a right angle. That is why definitely it should be an angle in a semicircle. So P is simply forming a semicircle. In very similar way, on the other side also, if you are extending this one, you are getting a circle, locus as a circle with AB as a diameter. Therefore, whenever this condition comes, angle APB 90 degrees, where P variable point and AB are fixed points, the locus will give you a result of circle with AB as extremes of a diameter. So here, but in case, one specific thing we have to remember while using this case, what is it is that we can choose P anywhere on the circumference here, except taking P at A or B. In case by choice, if we are taking P at A, then P, A and B will become collinear points, and collinear points will never give you 90 degrees. A contradiction arises. So in this locus, P can be taken anywhere on the circumference of the circle with AB as diameter, but we can't take P at endpoints A and B. So except these, the locus of P is giving a complete here circle points. In this case, if you have to find out the circle general equation, let us assume these 2 points given as x1 comma y1, x2 comma y2, and Px comma y, let us take a general point with standard point x comma y. Now angle APB is a right angle, then product of slopes, if the slope of this is m1, slope of PB is m2, product of slopes is -1, implies slope of AP y minus y1 by x minus x1 into slope of PB similarly y minus y2 by x minus x2 equals to, we are getting -1. On cross multiplying the denominator, y minus y1, y minus y2 equals to minus of x minus x1 into x minus x2. This implies transferring left side, x minus x1 into x minus x2 plus y minus y1 into y minus y2 equals to 0 will represent the circle equation with x1 comma y1 and x2 comma y2 as extremes of a diameter. This can be taken as the second frequently coming cases of circle standard equations. In the first case, we have derived the circle when the center and radius given. Now in the second case, we can able to get the circle equation when extremities of diameter of a circle given to you, x minus x1 into x minus x2 plus y minus y1 into y minus y2. Not only these two cases, many other cases frequently we find the locus as a circle. So let us see some other cases also apart from these two standard cases. Coming to the third one, let us imagine two perpendicular lines in the plane. They need not be coordinate axis, any two perpendicular lines we have chosen. And P is a variable point moving such that the sum of squares of its distances to these two intersecting lines, perpendicular intersecting lines, is always a constant. PL square plus PM square equals to a constant K. Whenever a variable point is moving such that the sum of its squares of its distances from two perpendicular lines is always a constant K, then locus of this point can also be taken as circle with the center as the point of intersection of these two perpendicular lines and radius as root of this constant given, because PL square plus PM square is given as K, which is equal to this SP square, then SP distance will become root K. So in such type of locus conditions also, we can say that the locus is forming a circle with center as point of intersection of these two intersecting lines and straight line is, and this root of K will be taken as radius of this one. Many cases we can avoid lengthy calculation in finding center and radius for this type of problems. Let me give you one simple example to analyze this case. Suppose you are asked to find center and radius of the circle whose equation is given as x plus y minus 2 whole square plus x minus y minus 1 whole square equals to 48 given. Just one simple equation is given, x plus y minus 2 whole square plus x minus y minus 1 whole square equals to 48. If we are asked to find the center and radius of this circle equation, undoubtedly this will form a circle equation, but now the question is, what is its center and what is its radius we have to trace out. For that, as you observe this one, it is almost very close to this standard equation. Okay, PL square plus PM square equals to K form. But the only difference is this PL and PM are representing perpendicular distance forms from a point to a straight line. That is why here, to get these two also in perpendicular distance form, as we know already, perpendicular distance from a point to a straight line is modulus ax1 plus by1 plus c by root of a square plus b square. To write this in that standard form, we require additionally the denominator part root of a square plus b square. Here, root of a square plus b square, 1 square plus 1 square 2, root 2. Here also root 2. So in this equation just we are missing the denominator part root 2 whole square. Root 2 whole square is 2, that is divided both the sides. If you are dividing right side also with the same, so you are getting this value as what? 24. So now this is a complete circle equation giving in this form. PL square plus PM square equals to K form you are getting. This is representing a circle equation whose radius is root of this K. Radius of this circle equals to root of 24 will be 2 root 6 units will come. Not only that, if you have to find out the center of this one, we need not expand the complete equation. Avoid expansion, and we know that if that is representing a circle, point of intersection of these two lines will give you straight away the center of this one. So solving the given two lines, x plus y minus 2 equals to 0, x minus y minus 1 equals to 0. Solving these two lines, here y minus y get cancelled on addition, 2x minus 3 0, x will be 3 by 2 and y will be 3 by 2 minus 1 will give you what? Y by 2. Therefore, center of this circle will be 3 by 2 comma 1 by 2 and radius of this circle given is 2 root 6 units will come. So, if you have the conceptual idea of this type of locus cases, we can avoid lengthy calculations in such type of questions. The very common complaint in geometry problem solving cases by most of the students is its lengthy calculation part. That is why wherever required, we can cut down the steps by introducing some conceptual techniques. Here, shortcut cases we have two types, conceptual techniques and shortcut formulae applications. Always we try to avoid formulae oriented applications, but this type of conceptual techniques we can retain permanently, and we can also effectively apply this one whenever required. In this geometry session, we are going to learn many such shortcut conceptual techniques. That is very essential thing one requires to cut down the lengthy calculation part in geometry. Okay, now let us see some other standard forms of circles. Already I have given you three cases when the center and radius given, first case. Second case, when extremities of diameter given for a circle, how to find circle equation, also we have seen. Now the third case, whenever a point is moving such that sum of squares of its distances from two perpendicular lines is a constant k, then its locus is always representing a circle equation. Okay. Before entering into other cases, just let us analyze all these three cases, how we are getting this circle equation standard form. If we simplify, what are the terms we are going to get? After that, we can enter into some more locus cases. Now, in the first case, when center h comma k, radius r given for a circle, we have taken its standard equation as x minus h whole square plus y minus k whole square equals to r square, which is simplified to get this form: x square term, y square term, then you are getting minus 2hx, which is x term, then y term minus 2ky plus rest of all the terms h square plus k square minus r square. After transferring r square left side, you are getting the terms in this way. If you observe closely this equation, it contains x square term, y square term, some x term, y term and constant term. Whatever the other form you are taking, finally circle will contain in general these terms: x square term, y square term, x term, y term, constant. That is why in general we can take a circle equation as x square plus y square plus some coefficient 2g into x, some coefficient 2f into y plus constant c equals to 0. This can be taken as the standard form of a circle. If it is representing a circle equation, we must analyze what is its center and radius for this. To get its center and radius, we should convert it into center radius form. It is very simple from these equations. Write x square 2gx terms together plus y square 2fy terms together and transfer this constant right side, becomes minus c. To make it a perfect square like x minus h whole square, here what is additionally required? Just g square is required. I am adding g square here, adding f square here. The same are added right side also to balance the equation. So after addition, the equation has converted into the form x plus g whole square. First three terms are in the form of a plus b whole square plus y plus f whole square equals to g square plus f square minus c under root whole square. If we write, then it is completely in circle standard form, center radius form. If we are comparing this equation with this equation, you are getting the center equals to x minus of minus g, we can write this. So center abscissa is minus g. Similarly, ordinate is minus f. The center of this circle is minus g minus f, and the radius equals to g square plus f square minus c under the root. So here circle standard form x square plus y square plus 2gx plus 2fy plus c equals to 0 if we are considering, then its center and radius will be taken as minus g minus f and radius g square plus f square minus c under root. There is nothing confusion regarding this center, but here the radius is expressed as under root something here. That is why we can analyze the cases of this circle, because under root negative part if you have, sometimes it may become imaginary also. That's why we can analyze this circle nature on the basis of this under root value. Here if g square plus f square minus c greater than 0, then it is representing a real circle. If this value is equals to 0, the radius is 0, then the circle can be taken as a point circle which is real on the plane. That's why this can be taken as a real point circle. And finally, if this value is less than 0 under the root part, then this whole root will become an imaginary part. Then the circle can be taken as an imaginary circle. We are getting an imaginary circle with real center and imaginary radius. Unlike to the other curves, imaginary circle contains center real, means we can locate the center of an imaginary circle also on the plane. Okay, we cannot locate the circumference, but in case of center, clearly it is a real point existing in the plane. That's why in case of imaginary circle, we can locate the center very comfortably on the plane. So because of this particular reason, we imagine that this imaginary circle is following all other properties like real circles following. So now and then we find the questions containing these imaginary circle equations also. So don't confuse with this particular part. So on the whole, based on g square plus f square minus c, we can categorize the circle into three cases. When this part is greater than 0, real circle, equals to 0, real and point circle, less than 0, it is an imaginary circle with real center and imaginary radius. So here now onwards we can consider this standard equation, because as I told you already, to avoid lengthy calculations every time, we can cut down the steps by using some shortcut approaches also. Now let us take this standard equation as S equals to 0. This S stands for circle equation. Now onwards we can use it as standard equation of the circle. So coming to this standard equation of the circle, S identically equals to x square plus y square plus 2gx plus 2fy plus c equals to 0. Compare it with the previous second degree non-homogeneous equation in x and y, that is ax square plus 2hxy plus by square plus 2gx plus 2fy plus c equals to 0. I told you already very clearly that this equation is representing various conic sections depending on different cases. Now in particular, when you come back to this circle's case, suppose if this equation is representing a standard circle equation, definitely this must be written in the form of circle standard equation. To get this in this standard equation, the compulsory condition we are finding here is what? X square and y square coefficients. Here x square, y square coefficients both are equal to 1 and 1. If you take the entire equation multiplied with some k, you will get kx square and ky square also. So that is why compulsorily x square and y square coefficient should be equal. Here x square coefficient a, y square coefficient should be equals to b. Here the necessary condition for this second degree non-homogeneous to be representing a circle equation is a should be equals to b. And observe this case. Here in standard equation of circle, we are not finding this xy term. It must be disappear. It is possible if and only if taking h equals to 0. So that is why if this equation to be representing a standard circle equation, we have to take x square and y square coefficients equal a and b, and also xy coefficient h equals to 0. Applying this h equals to 0 and taking a equal to b, it can be reduced to the form, this equation can be reduced to the form ax square plus, now I am writing b as a, ay square, eliminating h, 2gx plus 2fy plus c equals to 0. Coming to its center, or just if you divide with a, x square plus y square plus 2g by ax, 2f by ay plus c by a equals to 0. Now compare this equation with this equation. Its center will be minus g is replaced with g by a, f is replaced with f by a, and the radius of this will be under root g square becomes g square by a square plus f square by a square minus constant c replaced with c by a, taking LCM g square plus f square minus ac by a square, which also can be written as g square plus f square minus ac under root by root of a square, as we know always mod a. So radius of this circle will be g square plus f square minus ac under root by mod a, and center of this circle is minus g by a minus f by a will come. So if this is taken as standard form of circle equation, the center is minus g minus f, radius g square plus f square minus c, and if this second degree non-homogeneous equation in x and y representing circle standard equation, then center will be minus g by a minus f by a, and radius will be g square plus f square minus ac under root by mod a. A very standard equations to be noted here are these two. After analyzing the first 3 or 4 cases of circles, now let us enter into a very frequently coming other case. Let us imagine 2 points A and B, fixed points, and P is a variable point moving in such a way that the ratio of its distances from these two fixed points, PA by PB, is a constant K, where this constant k not equals to 0 comma 1. If this is equals to 0, PA by PB equals to 0, then PA equals to 0 will come, then A, P both will be coinciding, then P will become fixed point A. So that's why I am taking out that case separately. Coming to the second condition, not equals to 1. If A and B are two fixed points, P is a variable point moving such that PA by PB equals to one special case. You are getting P will be equidistant from these 2 points. Wherever P you take, that is equidistant from these two. If you join all such points, the locus will give you the perpendicular bisector of given 2 points A and B, which is not a circle will come. So, leaving these two special cases k not equal to 0 and 1, rest of any other cases, if you are taking k any real number other than 0 and 1, the locus of P in such cases will always represent a circle, which is called the Apollonius circle. To analyze this Apollonius circle in detail, we can take the help of previous standard form of the circle, general form of circle. Here, let us imagine these 2 points as x1 comma y1, B as x2 comma y2, and this is taken as some general point x comma y. Now apply this condition PA by PB equals to k. Let us see how does this equation converts. PA by PB equals to constant k implies PA square equals to k square into PB square. Substituting the values, PA square x minus x1 whole square plus y minus y1 whole square equals to k square into PB square, distance between these two, x minus x2 whole square plus y minus y2 whole square. Simplifying this lengthy equation, writing these similar terms together. In this, the first term is x square into its coefficient k square. Here x square coefficient is 1 transferred right side, will become k square minus 1 x square. In very similar way, y square coefficient, here k square, here 1 transfer right side becomes minus 1 into y square. X terms, minus 2x x2 into k square, take minus 2x common. Here you are getting k square x2. This is minus 2x x1, transferring right side becomes plus 2x x1. If you take minus common, again inside will become minus x1. Similarly, y term, minus 2y into k square y2 minus y1 plus some other constant terms equals to 0. We need not bother about these constant terms. We write all constant terms together. Once observe this equation of this locus we are getting. Are you getting x square coefficient and y square coefficient both are equal or not? And xy term disappears in this. Therefore, according to the previous case which we have discussed just now, x square and y square coefficients equal and xy coefficient not equal to 0. Hence, it always represents a circle equation whose center is, just now we have derived the formula to this, minus g by a minus f by a. Minus g will be plus k square x2 minus x1 by k square minus 1. k square y2 minus y1 by k square minus 1. So clearly this locus is representing a circle equation. If A, B are fixed points like this, the locus of P, if you take like this, the locus is giving a circle equation. Every point on this circle will satisfy the condition PA by PB equals to constant. Not only that, we have to observe a very important other fact, that its center, if you analyze, is it external section formula for x1, y1 and x2, y2 points or not? This point is dividing x1, y1 and x2, y2 in the ratio k square is to 1 externally according to mx2 minus nx1 by m minus n formula. So we find the center of this circle somewhere here, which is collinear with the points A and B. And not only collinear, this C is dividing these 2 points given in the ratio k square is to 1 externally. So center of this Apollonius circle divides these two in that ratio k square is to 1 externally, whereas any point on the circle will satisfy the condition PA by PB equals to constant k. Therefore, whenever you are getting this locus case PA by PB equal to k other than 0 and 1, you are getting the locus as a complete circle equation, which is called the Apollonius circle, whose center is collinear with the given fixed points A and B, and the center of this Apollonius circle is dividing A and B in the ratio k square is to 1 externally. This is a very frequently coming other case which concept is very much useful in solving some of the typical areas. Now coming to one more case where you are getting this circle, let us imagine some fixed points in the plane somewhere, some A1, A2, A3, A4 like this. There are some points given to you. Let us take n number of points here in the plane which are fixed in the plane. I am taking the coordinates of all these n points as ai, xi, yi, where I is taken 1 to n. N fixed points are given, and P is a point chosen, variable point chosen, such that PA1 square plus PA2 square plus PA3 square plus so on PAN square equals to a constant k. A variable point P is moving in such a way that sum of squares of its distances from given n fixed points is always a constant k. Here also the locus will give you always a circle equation. Instead of analyzing diagrammatically this case, we can analyze it more comfortably with the equation standard one we are going to get. Simplifying these all equations, let us analyze this. Let us take this point as x comma y. Taking these equations here, PA1 square x minus x1 whole square plus y minus y1 whole square. Instead of writing this whole, why can't we take summation? Here, if you want, we can take this one as I, this one as I, and I is taken from what to what? 1 to n, equals to how much we are getting? K. Simplifying, first term is x square. Sigma x square is added n times. You are getting the summation as nx square, and obviously here also n y square. Very clearly we are finding x square and y square coefficients equal, and there is no chance of getting xy term in the expansion. So undoubtedly this equation will represent a circle equation. To have its center comfortably, let us analyze the next term. minus 2x xi summation. So we can apply summation to this xi minus 2y summation yi plus summation xi square plus yi square constant term xi square summation yi square summation minus constant k equals to 0. In all summations we take I from 1 to n. Here I is taken from 1 to n, here I is taken from 1 to n, here also I is taken from 1 to n. Now if you analyze this equation, how is this? Just observe here. X square y square coefficients are equal and xy term is 0. Definitely it represents a circle whose center will be minus g by a minus f by a equals to minus g by a will be summation xi I taken from 1 to n divided by a is n and summation yi by n, which is giving you the average of abscissae and average of ordinates. Therefore, whenever a variable point P is moving in such a way that the sum of squares of its distances from n fixed given points is always a constant k, then its locus is always a circle whose center is average point of the given n points, whose abscissae is average of given abscissae and whose ordinate is the average of ordinates of the given n points. So this is a very frequently coming other circle locus case. Like this, many cases, whatever we have discussed, case 1 we have discussed the circle with center and radius given. Coming to the second case, whenever ends of diameter given to you, in that case how to get circle equation we have seen today. Third one, here when two perpendicular lines are given, the locus of a point moving such that sum of squares of distances to perpendicular lines is always a constant k, there also you are getting the locus as a circle equation. And we have discussed the general form of a circle in various cases. Okay, non-homogeneous, if it is representing circle, what are center, radius, and general form of circle, how to find center and radius, all these we have seen. And this is another case also we have discussed. And in previous case I have given you the definition of what? Apollonius circle also. So these are like this, very frequently we find the locus of different cases giving you the conclusion as a circle equation. That's why you can understand the importance of this circle locus various cases. You must have a clear conceptual idea where you are getting circles in different cases. Once you are getting command on these conceptual locus cases, its applications will be very convenient in solving problems. We can avoid unnecessary steps in calculations most of the cases. So these are the first 5 cases we have discussed. Now let us enter into a very important other part regarding the notations we are using in geometry. As I told you already in the very beginning, a very common complaint we are finding in geometry problem solving by most of the IIT JEE aspirants is its lengthy calculation parts. We can avoid this lengthy calculation frequently by using some shortcut approaches, conceptual techniques. Apart from these, we can also use notations for these lengthy equations. Let us see how to get these notations for various curves in geometry. Now let us see how to form various notations in this geometry second degree non-homogeneous equations. Or before that, let us see standard equation of circle. As I told you already, if we take S as x square plus y square plus 2gx plus 2fy plus c. This circle standard expression, with this we start writing the notations. In this equation, except the constant, all other terms are having variables. Now I am writing these variables either as product of variables or sum of variables. For example, x square I can write it as x into x. Y square I am writing y into y. 2gx written as g into sum of 2x plus 2fy written as f into y plus c will be kept as it is. Now in this, except the constant term, every other term is containing either product of two same variables or the sum of same variables. Now if you are replacing one variable in this with x1 or y1, that can be taken as the notation s1. For example, here s1, if you want, replace one of these x with x1, one of y's with y1, g into x plus x1, f into y plus y1 plus c. This notation is called s1. If you are replacing one with x2, y2, it can be denoted as s2. x2 plus y2 plus g into x plus x2, f into y plus y2 plus c. If you are replacing both of them with x1, y1, that notation is called s11. x1 into x1 again becomes x1 square. y1 becomes y1 square. x1 plus x1, 2x1 into g, 2gx1, 2f plus c. This notation taken as s11. Similarly, we can write s12 also. First one with x1, y1, second one with x2, y2, simultaneously we write. x1, x2 plus y1, y2 we write, plus g into x1 plus x2, f into y1 plus y2 plus c. This notation can be taken as s12, and one can guess very comfortably that this is also equals to s21. So we can write the notation s12, s21 both as same. So like this, we can write various notations in terms of s. And we are going to get many of the results of circle standard forms in these notational terms, and that will be carry forward to the coming chapters like parabola, ellipse, hyperbola and all those. While writing notations, we get a small confusion regarding xy term. If we are developing notations for circle standard equation, it do not contains xy term. If we enter into the other chapters like parabola, ellipse or hyperbola, there we may have to write notations once again. There we require the notation method how to write for xy term also. That is why let us see how to write xy term various notations. If you are taking s as xy, write this xy as half into 2xy, that 2xy written as xy plus xy. We follow a little bit different procedure for this comparing to other cases. That's why I am writing it separately. Now s1, if you want, half into, in this y replace with y1, in this x replace with x1. xy1 plus x1y can be taken as s1. s11 is very common, like the previous one. Replace x and y in the given equation with x1, y1. That is called s11. If you want s22, x2, y2, we can write in similar way. If you want s12, here replace it with x1 and this one with y2, and here x2, y1. This is the way of writing notations for this s equals to xy. In this chapter, no question of getting this term. Circle entire chapter we do not use this, but for the coming chapters we should have a clear idea of how to use notations for this xy term. That's why I'm introducing those cases also here only along with these cases. This is the way of writing notations which can help us in reducing the lengthy writings of these geometrical equations.